And we welcome our two esteemed colleagues, scientific guests of the event of today. So let me welcome first our external guest, Professor Guido TONELLI, physicist from CERN and University of Pisa. He was the spokesperson of one of the two experiments, CMS, at the time of the discovery of the Higgs boson, and therefore awarded the International Fundamental Physics Prize, Enrico Fermi Prize of the Italian Physical Society, and the Medal of Honor of the President of the Republic for being, udite udite, the latest example of a tradition of excellence that began with Galileo Galilei and continued through scientists such as Enrico Fermi, Bruno Pontecorvo, and Carlo Rubbia. And Guido TONELLI. He published various books that we have here, and we invite you to visit in Italian and German. Genesis, Chronos. I give you just a short title, but the German translation is more complex than this. And today we'll discuss his latest work that's called Matter. Our local guest, Luciano REZZOLLA, professor at Goethe University in Frankfurt, teaches theoretical physics and is actually the director of the Institute for Theoretical Physics at our university. He's a photographer of the black holes. The first picture in the world that came for a black hole carries his name, with a leading role in the Event Horizon Telescope, for which astrophysical complex objects such as black holes could be for the first time imaged. He has received also a number of prizes. Here we want to recall the Frankfurt Physics Science Prize and the Einstein Medal. His book about gravity, Die unwiderstehliche Anziehung der Schwerkraft, eine Entdeckungsreise zu der schwarzen Löchern, was published also in German, and we have it here today for you for further reading. So this is an interesting topic together with matter and gravity. One could not exist without the other. You remind us that the word matter, Guido, carries the root of the word matter, mother. But what came first, gravity or matter?
A very good question. Good morning, everybody. I try to answer first to the question of the question, who came first. What we think today is that our universe is made out of two simple components, two ingredients. So if you want, go back home and produce today a universe. I give you the recipe. I cannot give you the ingredients, but the recipe is quite simple. Just mix together mass energy and space-time, basically. A universe, our universe, is made out of these two ingredients. We usually tend to see only stars, galaxies, dust, planets, human beings. That is mass energy, the visible part of the universe. But there is another ingredient which is as important as the first one, and is the space-time. And a great scientist 100 years ago or so explained us that basically once you have mass energy and space-time, there is a distortion of the space-time due to the presence of mass energy. Whenever there is mass energy, space-time is bent. That means that if something is bent, is distorted, is not a concept. Can you immediately realize that he was maybe not aware, but he was already thinking of something material that has some material consistence. Otherwise, you cannot be bent. And this distortion of space-time is what we call gravity. It's another way of looking at gravity. So it's very difficult to say who comes first. I would say they come together and they form the universe.
Gravity. Gravity is the only interaction, Luciano, that humans perceive all the time. And in your book, you remind us that even small babies have a perception of that without being ever told. However, for centuries, we had looked at it, and by now, our understanding we think is good, but still, in your book, you let us think that it's still mysterious, that still has something that we have not fully understood. What are the mysteries with gravity, and what is still to be discovered?
Okay, well, thank you for the question, and thank you for being here. I can imagine it's not what you would normally do on a Sunday morning. So you're right. Gravity is really a different type of interaction. Now, in physics, we think there are four main interactions. There is the strong interaction that keeps the most elementary particle into other particles, which we call neutrons and protons. Then there is the nuclear force that keeps these neutrons and protons together in nuclei, like hydrogen or helium or uranium. Then there is the electromagnetic force that regulates things like electricity, light. And then there is gravity. And gravity really is different in many respects. And first of all, it is the only interaction that we experience. Right now, you are sitting. You have walked to come here. And for doing this, you have consciously interacted with gravity. When you make a movement, your brain is thinking about gravity because it has to spend energy against it. While you don't think about nuclear force, or you don't think about the strong force. It's something that happens independent of your conscience. And this interaction with gravity is very special for us. And is so deeply rooted in our genetics that we know about gravity even before we are born. Now you may say, how do you know this? Well, it's very easy. It's discussed in my book. You take a very small baby, extremely small, just a few seconds after being born, and you drop him or her. Well, you don't really drop. You just let this baby experience an acceleration. And the baby will react with an instinct, which is called the Moro instinct, by putting out the arms like this and trying to grab to something. That means there is already something in our brain that tells us there is gravity. And yet we are completely helpless. We don't know we hardly know how to breathe, okay? We just learned a few seconds earlier how to breathe because we didn't breathe before. And yet our brain know about gravity. So gravity is deeply rooted with us, and it's very hard for us to get away from it, okay? The only way in which you can get away from gravity is jumping down a cliff or a building, something we normally don't like to do. But we always think about it, okay? It would be in fact, I think that's why everybody would like to go on the space mission, on the space station, okay, in the International Space Station, because there is no gravity there, and we would be just floating around weightless. Now, Einstein explained that the way we understood gravity is different from what we normally thought. And Newton told us it's a force, you need two objects, different masses, you calculate the distance, you know the strength. And it's instantaneous. We think that's unacceptable in terms of our understanding of physics. Nothing can be instantaneous, and actually has to do with geometry. So this is a very different way of thinking about gravity. In all the other forces, we think there is some interaction mediated by particles are exchanged so that this interaction manifests. In gravity, we think it's curvature, as Professor Tonelli said, space-time curvature, a very completely different concept. In fact, it's a mathematical concept. In fact, all of the mathematics behind Einstein's theory comes from mathematicians, not from physicists who did experiments and so on. It's, by the way, Italian mathematicians like Ricci or Levi-Civita or Codazzi but together with other German, like Riemann, who had defined all of the geometric properties of the theory, and then Einstein just grabbed all of this knowledge in mathematics and said, okay, gravity is just the way we realize that there is curvature. So curvature is there, it's produced by matter or energy, and gravity is a manifestation of this curvature. It's the way we can see that there is curvature. Now, coming to your question, sorry for being such a long introduction. Well, gravity, as explained by this theory, has a number of very bizarre consequences, and one of them is black holes. Black holes are, problematic for the theory. They say that there is a region of space-time where you can go in, but there is nothing that comes out. And we don't like this as physicists because we like to be able to do experiments everywhere. And instead, inside a black hole, we can do an experiment, but we cannot tell anyone about this. So there is a region which is off limits for our science. That we hate this. Okay, yes, scientists, we want to be able to tell about anything, even the first instant of the universe. And instead, this theory says no. There is a region. It's like opening a door. You can open the door, enter the door, but that's it. The second thing is that this theory predicts singularities. Again, this is something we really don't like. We like to have something where we can calculate everything everywhere. And this theory, as it is doesn't give us this opportunity. At the center of a black hole, there is something where we cannot calculate. So this is a beautiful theory, one of the most beautiful theories and most revolutionary theories, but it has problems, and these are just two of them.
Can I add my view on gravity, because I'm really embarrassed. Whenever we talk of forces in general, we are scientists, so we come from a century of discoveries, of progress and results. But it's embarrassing to admit that the most popular force, which is gravity, the one that you experience every day, we have not, we don't know basically nothing about the real, to explain a force, we need to produce what we call a quantum description of the force. And what is embarrassing is that we have been able in the last century to provide a quantum description of all the other forces apart gravity. Is not embarrassing this? It's completely nonsense. The force that was discovered first, because gravity was known by the old Greeks, is still there, lacking an interpretation, a real interpretation in terms of physics description. The other forces, the electromagnetism, or the weak force, or the strong force, all the forces that were discovered in the last couple of centuries, for those we have a quantum mechanical description. It's not embarrassing for modern science. So there is something really hidden there, which is probably, I have the impression that on one end we are frustrated. On another hand, I see the thing from another perspective. The way in which we'd be able to quantize gravity, really to have a quantum description of this force, we might discover something so surprising that would lead us to additional technologies. I have the impression that for example, the breakthrough in technologies that we have been able to develop, having understood quantum mechanics and relativity, the beginning of last century, from this break of paradigms, we have developed a huge amount of technology. Having quantized the electromagnetic force or having understood the behavior of matter at a microscopic level, we have built cellular phone diagnostic tools in the hospitals. We have been able to see matter, no? But we are not able today to have the same description of space-time, which is gravity, basically, no? So imagine this, that the modern science have made a huge amount of progress on one element of the universe, mass energy. Now, we have a microscopic description of mass energy, and we lack a macroscopic description of space-time, and this is the reason why we lack a quantum description of gravity. No, the two things are somehow connected. And I have the prejudice, which is a dream, that the young student that maybe in 20 years from now or 200 years from now will be able to solve the problem that Einstein was not able to solve, or Stephen Hawking, to really have a quantic description of gravitation, will open a new world. Because once you have a deepest knowledge of the inner structure of space-time, which means you really master gravity, you might develop from this knowledge a huge amount of additional technologies. So hidden in this mystery of modern science might be a completely new world. Maybe it could be a dream, maybe, but I like to have this dream, let's put it this way.
So describing an interaction in physics means, you show us in your book, assigning a particle that carries the interaction between the two particles that feel the interaction. So this description of an interaction, a force, as an exchange of a mediator particle. Does it work for gravity, and what is the particle that we have to associate with that?
Well, in principle, yeah, you can think that by analogy, you can build a theory of gravity where there is this graviton that is a particle that is exchanged. But this theory has a number of problems, and despite having tried to look at this theory for more than 50 years now, a quantum mechanical description of gravity, we really are not able to come up with something that is satisfactory. There are a number of reasons why this is the case, and I share the view of Professor Tonelli. I think there's going to be really a jump in our understanding of the world, the time when we will be able to interpret gravity in terms of quantum mechanics, or maybe change quantum mechanics so that we can provide a gravitational description of all the other forces. But it's clear that there are two different ways of explaining things, and gravity is really different. And yeah, this is embarrassing. This is, exciting in a way. Young people, if young people had already, if we had already solved this problem, there would be no excitement from the young people in trying to solve it, right? So I've always liked to think that there are open problems, because otherwise, if there are no other open problems, what do people with, talent and great intellect think about? So, yeah. We are being very altruist and leaving this problem to the younger generation.
Let me connect this to the revolution that occurred when the description provided by Newton of two bodies, a distance, changed to the description of relativity with a curvature of the space-time. Is gravity an interaction, or is gravity a curvature? And what is the difference between an incomplete theory and a wrong theory? Are we seeking for such a new revolution again in order to come up with a quantum description of gravity?
So I must say that when the revolution took place in 1915, that's when Einstein published his equations, this was a revolution no one realized. In fact, no one took Einstein seriously. Einstein was very famous, already had received a number of distinctions. I can't remember, I think he already had the Nobel Prize at that point. And nobody debated that this was, right. It just was thought to be useless and pointless, because the changes that this theory implied in all of our understanding were so little that people just thought, okay, this is probably right, but irrelevant for all we know about physics, because it produces slight changes that are sometimes not even measurable. So at the time when the theory was published, all the good scientists were excited by another theory, which was developing at the time, which was quantum mechanics. So no one paid attention to Einstein. There was one exception, a Frankfurter, Karl Schwarzschild. He came up with a solution a few months later. And again, Schwarzschild didn't understand what he had found. He asked Einstein. Einstein said, yeah, this looks right. I have no idea what that means, because it was the black hole solution, okay? The black hole solution found by Schwarzschild 6 months later. And this means that, some of the predictions of this theory are so far away from our experience, so far away from what we can experiment on Earth, that people tend to forget and put it aside, because anyway it's irrelevant. And things became, could not be postponed anymore in the 60s. In the 60s, there was a revolution in terms of astronomy. X-ray astronomy was, starting. People sent satellites out in space, and they thought, okay, these satellites will see X-ray emission from the sun. That's going to be the largest source. And actually it wasn't. The largest source was a teeny tiny object in our galaxy. And people thought, okay, how can this be? This cannot be a star. It was way too small to be a star. And you know that it's small because it's varying very, very rapidly, millisecond variability. At that point, people were forced to think, okay, this is not a star. But what can it be so massive and so small? And people got back to the Einstein idea and Schwarzschild solution to realize, actually, maybe this is it. And that's when, we start realizing that this theory is actually right and useful, and nature is using it all the time. Maybe not on Earth, where it's pretty much irrelevant, but in space, this is where, this is what regulates gravity in outer space. And so, to come back to your question, what is a wrong theory? Well, there is no right theory. In physics, there is no right theory. There is just a good enough theory to describe what we know. So all theories, if you want, are incomplete. And I hope they will always be incomplete, again, for the same logic. If they are incomplete, means I need something else to complete them. And so I can think about something new. And Einstein theory is certainly incomplete, is much better than what we knew before with Newton, is certainly right for all of the observations, but has problems. And this is what lays ahead in the research on gravity, fixing these problems in Einstein theory.
In particle physics, our now most complete theory is probably the standard model. So what is the standard model and what is beyond the standard model? The expression beyond the standard model, that sounds so colloquial even to us here, but it's now an entire field of science. So
again, I'm even more embarrassed than before talking about the standard model. Standard model is a beautiful theory that describes matter, basically. The matter component of the universe, which is stars, galaxies, planets, dust, hydrogen, human beings, plants, rivers, stones, whatever, can be described by a few components. Limited amount of elementary particles that interact among them using other particles that carries the forces, the interaction. And there is a hierarchical structure that allows us to explain quite well, quite easily, the composition of each material component. No? So we know that everything is made out of atoms, basically, or nuclei around which there are electrons orbiting, so we can describe the electrons, we can describe what is inside the nuclei. which we call protons and neutrons. We can describe what is inside protons and neutrons that we call quarks and gluons. All this is well described, and we can describe the wings of a butterfly or a crystal, basically using the same mathematics. But the problem is that this description applies to an embarrassing small amount of the material composition of the universe. So this is the embarrassing part. No? I'm very proud of the Standard Model. We have proven all the components. We have discovered the Higgs boson. We have celebrated with champagne all the discovery. But then we should realize that this description applies only to 5% of the universe. So if we consider the material component of the whole universe, only barely 5% can be described using the Standard Model particles. No? So the rest is dark matter. Maybe we describe later what it is. Is an elusive component which keeps together all galaxies, including ours. Is here. Here I have grasped a small amount of dark matter, but I have no idea, there is no particle of the Standard Model that can account for the dark matter. So we even don't know if it is particle or something else. So complete ignorance, and even more ignorant on the dominant component of the mass of the universe, which is dark energy. So we transform in mass the energy, the positive energy that brings to the expansion of the space-time, an accelerated expansion, and at the end, this contribute for 2/3 of the mass of the universe. So in all, the Standard Model of the elementary particle describe only this small 5% of the universe. But in addition to this is only a part of the story. Does not include gravity. Again, very embarrassing. So we describe the 3 major forces, but we ignore gravity. Gravity is not part of the Standard Model. In addition, within the Standard Model, we have a huge amount of questions, of mysteries. For example, we don't know exactly what is giving mass to components that are around in the universe. We call neutrinos, very light components, very gentle components of the material part of the universe, and we have no idea what is the mechanism that gives them masses, for example. We don't know why our universe is a matter universe, where all the antimatter that we thought at the beginning was produced initially in equal quantity, why, how has disappeared. We don't know, for example, why we have 3 families of particles. All these are huge mysteries. Another example I give you, we have discovered the Higgs boson 12 years ago, and we have understood the mechanism that gives elementary particles the mass. So now we can describe this mechanism. We have equation describing this interaction, this form of interaction. But for example, this particle is so strange that maybe there is something hidden there. The Higgs boson is the only scalar particle. It's probably the simplest particle one could imagine. If I ask a kindergarten kid to describe an elementary particle, he will do something similar to the Higgs boson. He is described only by the mass, its mass. There is no other quantum number, no other property. All the other particles have other properties that we call the spin, we call the charge, we call... the simplest particle is the most important one. It's not strange. In addition, there are quantum mechanisms that, in some sense, tend to destroy particles unless they are protected by some mechanism. And these mechanisms are available for all the other particles. They are not available for the Higgs boson. So we don't understand why the Higgs boson is there. Because it should explode. Its mass should go to TV, should increase, should become fatter and fatter due to known quantum mechanism. And so there is something protecting this huge particle from becoming unstable, and we don't know what it is. This is why we think that there is something beyond. No? There are other particles that are not within the standard model. That the standard model of particle probably is incomplete, is a theory that will be valid up to a certain energy. Beyond this energy, we might discover other particles or other interactions that should be incorporated in another vision, which is larger than the standard model, more complete, and will include the standard model as a low energy case. No? So we are really at the beginning of a long story. We are not at the end. The beginning of this story is what we have achieved today, and the end will be written by a young generation of scientists that will continue this work.
So the feeling that we know only 5% of our universe is really unbearable. You would agree with me. This dark matter, essentially we need to postulate it for, so the main argument is gravitational reasons. But Luciano, is this the only possible explanation?
So maybe just for those who are not very familiar with this concept, dark matter. What is dark matter? We look at the sky, not today, but we look at the sky and we see the sun, and we see that the sun is emitting light. So we immediately associate light with matter. We look at the night sky and we see little dots. These are also stars, and we associate this light to matter, to the presence of something that produces light. So we think, or at least people would think about 30 years ago, people thought all the matter in the universe is the one we can see, is what is called the visible matter. But then something, messed up this conception. People start looking and measuring how stars move in a galaxy. And they started with our galaxy. And if you think about gravity, as we learn at school, you would expect that if there is a given mass in the galaxy, then the velocity of stars goes down as you move outwards with a precise law. That means, a star which is at the edge of our galaxy should rotate very, very slowly. Vice versa, a star that is in the middle of our galaxy, like us, should rotate faster than the one at the edge, but slower than the one near the center, and so on and so forth. But then the surprise came. In our galaxy, the velocity of star doesn't go down. Even the star which is further away from us is moving as fast as we are. Okay? This became a real crisis when people realized that almost all galaxies have this problem. So the stars at the edge of a galaxy move faster than they should. Okay? How do you solve this problem? Well, there are two options. The first one is you say, okay, maybe there is gravity, but I don't see it. There is more matter in a galaxy. It's just that the matter I am measuring, which is just summing up all of the mass of all the stars in the galaxy, is not all. There is more in it. And because I don't see this matter, it's not producing light, I call this dark matter. The second option is gravity is wrong. Your theory of gravity is just wrong. The right theory of gravity should tell you that as you move further out, the velocity should not go down, but should go up. So what is the status of our understanding nowadays? Well, the jury is still out, but there is so much evidence that there is dark matter and that gravity is right. I mean, gravity as proposed by Einstein is right. How do we know this? Well, dark matter does a very interesting effect, which is called gravitational lensing. What does it mean? So I need to take you a step back. One of the predictions of Einstein's theory, because space-time is curved as a result of presence of matter, light doesn't propagate on straight lines. So light can be bent, and this means that if there is a source, a star, and in front of it there is something else, maybe another star or maybe something else, the thing in front of it will act as a lens. And this will distort the image, and surprise, surprise, we will see multiple images of the same star. So instead of seeing just one star, in certain conditions, we will see multiple images. Okay, it's like when you go in one of these, amusement park, and you go in one of these rooms with many mirrors, you see many images of you. Well, this can happen in the universe through gravitational lensing. We can see many images of the same star. And here is what makes us think that dark matter that gravity is right. We see this also when there is no matter that we can see. There is a lens, there is a clear lensing effect. We see multiple images of galaxies in this case, and yet there is nothing there that we can see. This is an evidence that the universe contains matter that simply doesn't emit light. It's dark matter. But this is matter. What is problematic is that, we don't know what it is. But we think it is matter, and it's not, a flow of gravity. Not everybody agrees with me on this. In fact, many don't agree with me. But the large majority agrees that it's really some form of matter, and Einstein is still right, and we just have to think about new experiments that will reveal what this matter is all about. So far, we don't know it, but it's there. And it's just a matter of using accelerators to find it.
Can I add, one of the problems, why it's so difficult to find a solution to the dark matter mystery, is that we have no idea if there are particles which are at the origin, what is the mass of this particle. So once we produce a certain search in the accelerator, which is my field, we basically use brute force. So we use another Einstein equation, E equal mc square, well known. We use energy to produce mass. So we produce, through collisions of high energy protons in our case, new particles whose mass is proportional to the energy of the collision. The higher is the energy, the higher is the mass that you can study. So we can study particle up to the maximum energy, from very low energy up to the maximum energy, which is defined by the energy of the accelerator. And in this particular case, in which we don't have no idea of the mass of the possible candidate for dark matter particle, the search is extremely difficult. Imagine that you are hunting for something, for an animal, but the animal could be a dinosaur or a virus or a bacterium, I would say, a small invisible element. Now, clearly, the hunt is extremely complex. In our case, we don't know if it is a very light object, extremely light, much lighter than all known particles we are dealing with, or much heavier, much more heavy than anything else we have been able to produce so far. So what we are doing, we explore all possible possibilities, but it is extremely difficult for thousands of scientists that are working on this subject today, in this moment. You have to imagine that there are thousands of scientists, some of them at CERN, some in underground laboratories, some in looking at telescopes, that are focused on the search for dark matter particles. No? And the day that will happen, someday, sometime, it will happen in the future. Sometime somebody will find something that can be explained only assuming that is a dark matter particle. No? But so far, this is not the case. And again, we have not been able to discover dark matter particles so far because we have not used the right tools, for example, because the particle has a mass which allows air to hide under known phenomena, for example, or the mass of the particle is so high that the current machine are not able to produce them, or there are there is something deeply hidden in this, and we are not able to, and we have to change theory, for example, another possibility. Nature has chosen another path, as it has happened in the past. This is the beauty of our work, no? That you start an initiative, you start a search. You don't know, not only you don't know if you will succeed. In most cases, you have to start with the idea that you will fail. Scientists are used to failures. It's our work to survive failures. No? But we are not even sure that the theory we are using will be correct, or the instruments we are using will be the correct one. So we live really in an environment which is full of doubts, but in some sense, this is the beauty of the work that we are doing.
So besides for terrestrial experiment to produce the dark matter here and eventually detect it, what are space tools that we can use to find dark matter in the universe? Can gravitational wave help us with this? And by the way, can you explain us what gravitational waves are?
Right. So, okay. So, what observations can help us doing is map where dark matter is, and that's actually something that people over the years have learned to do very, very well. So, when you go and look at the night sky, you can think, astronomers can show you and give you a name of all the little dots that we see. Some of them would be galaxies, some would be stars. And they also can tell pretty well how much dark matter is in very different parts of our sky, because they can measure this effect, gravitational lensing. But they don't know, okay? They don't know what is this particle. This is what we need to find out in experiments. We can only measure where it is, how much there is, how it is distributed, and from this come up with maybe possible origins. Another interesting way of measuring this could be from gravitational waves. So what are gravitational waves? We started saying that that matter produces, or the energy produces curvature. And we can think about this as a static concept. There is an object, any object, even us, we produce curvature. And so space-time around us is curved. But we also can move. And when we move, curvature will move with us. And so you can think that when very massive objects, very compact objects move around very rapidly, they produce perturbations in the curvature, and these perturbations then move like waves. Just like waves on a surface of a pond, they can be produced and propagate outwards. Okay, so these are effectively gravitational waves. These are ripples in the space-time fabric or curvature, and we can measure them through these very sophisticated experiments, which are gravitational wave detectors. They are amazing when it comes down to what they can do. They can measure differences in length which are 10 to the minus 21, one part in 10 to the 20. That's like measuring the distance between here and Neptune with the precision of an atom. It's just mind-boggling. Now, how can they help? So again, through gravitational lensing. If there is, the best source of gravitational waves are binary black holes or binary neutron stars. So imagine that there is in one direction a binary system of black holes that is producing some gravitational waves. Then, exactly like light, gravitational waves will move at the speed of light and feel whether or not the space-time between us and them is curved. And just in the same way, they can produce multiple images of the same gravitational wave event. So just like it happens for light, we could measure of the same event multiple images. And this could be, would we see this? Well, we would see the same object, exactly the same object, coming at different times, different arrival times on Earth of the same object. And this would allow us, again, to deduce what is between us and the source in terms of a length. So this sounds all very exciting. unfortunately, we haven't seen any gravitational wave event which has been lensed in this way, but there are searches. I think the problem is that we don't see too many gravitational wave events yet. Once we will start seeing hundreds or thousands a year, then this will become much more easy to detect, and then we will have another channel to test, dark matter.
Let's move towards the end and start thinking about your own question, because you will have time at the end to also ask questions. But let me try to start to wrap up. A bit more than 10 years ago, you were one of the scientists who discovered the Higgs boson, the famous God particle that gives mass to all other particles. Then 10 years later, you were one of the scientists who photographed a black hole, the singularity that destroys matter that ends up to be there. Are these two elements, the Higgs boson and the black hole, like the start and the end of the movie called Universe?
The Higgs boson really did play a big role at the beginning of the universe. We have to rewrite the books of physics in some sense, because we have discovered a mechanism that took place 10 to the minus 11 seconds, so hundreds of a billionth of a second after the Big Bang. From then onward, now we have data. We can describe the changes that happened since then. Previously, it is unknown. We don't know yet exactly what did happen. But from that moment on, we can describe with experimental data. So now we know that in this particular era, there was a particular field which is attributed to this particle that froze out, basically. The baby universe was in expansion, and during the expansion, the temperature was still huge, but during the expansion, the temperature was not enough to allow the Higgs boson to stay alive independently as a particle. And so it froze out, and the field changed completely the status of the entire universe. All the particles that were previously similar to the photons, so particle massless, so without mass, moving at the speed of light. If the universe would have been stayed the same, we would not be here, because basically there was no possibility for those particles to aggregate, to form matter. No? To form stable matter. It was matter, but not able to aggregate in stable forms. But this new field differentiated these particles, the particles that were interacting quite strongly with the field became massive. The particle that did not interact with the field stay massless, like the photon. The particles that interacted slightly with the field took a small mass, like the electrons that are flowing into in the circuit in this room. No? And this differentiation was extremely important for the following stages, because a few of the light particles that we call quarks, the light quarks, the lightest of the families of quarks, were able to condensate in stable forms. 3 quarks, light quarks, coupled by gluons, form the first protons and the first neutrons. And those are still here, because the lifetime of this form of matter is huge. We have not been able so far to measure the natural decay of a proton. It is exceeding by many orders of magnitudes the age of the universe. So, being able to form stable matter, our story could have begun. No? Because you form the first protons, neutrons, the first dust, the first stars, the first galaxies, the first planets, and so on. So the rest can be described. So really we have understood a critical element of our history. But as I was telling you before, once we have the answer to some question, this was a question open since 50 years, so since the 60s. There are other questions coming out. One I was alluding to you before, the real structure of the Higgs boson. Is really an elementary particle, or it is a composite element, for example? No? This scalar particle is the first one of a series of scalar particles. Now, is different from the others. Maybe it is the first element of a new family composed by scalar particles with the same simple structure that some of them might explain, for example, the dark matter or other phenomena that are puzzle for us. Is, for example, the Higgs boson decaying to dark matter particles? This is a thing we are investigating. Since the Higgs boson has these properties to couple with the particles to give them mass, we have to assume that he is coupling to the known particles, the standard model particles, but is able also to couple to the unknown particles, particles not yet discovered. So we have a sort of an antenna which talks with the particles that we know, and we measure all the communication, we are able to do it, but we should be aware that this antenna might talk maybe with a small amount of voice with the unknown particles. This is why, for example, we produce now, after having produced hundreds at the beginning to allow us to discover it, now we produce millions, and the program is to produce hundreds of millions of Higgs boson, because we want really to understand its properties. In some sense, it's like the gravitational waves that you were describing before. The discovery of yesterday is the tool for new discovery of tomorrow. So now that we know the properties of the Higgs boson, we use the Higgs boson as a tool for additional discovery. One of the secret hopes that we might be able to discover some very rare decays of the Higgs boson in dark matter particles. So far, this was not the case. We have not been able to see them. But again, nobody knows. Could be just a matter of time, or just a matter of having enough energy to be able to see it.
And Luciano, is the black hole the end of everything? And by the way, every time they switch on a new particle accelerator, there are newspapers full of will there black holes be created at CERN, at Brookhaven, maybe at GSI here?
Next one. You should bet on it.
So, from my point of view, because every description of physics is incomplete, these events, Higgs discovery, first black hole image, these are just interesting episodes of this, never-ending series. These are particularly important because, they teach us a lot, and they really set a before and after. In the case of this first image of a black hole, what we've done, I think, is valuable from this point of view. And actually, brings us back to Galileo, the origin of everything, of our scientific method. Galileo was a very pragmatic person. He didn't want to end up in endless, time-consuming philosophical discussion about what he called massima, principii massimi. Very complicated, philosophical, pointless discussion about where we come from, what are we here for, and so on. He was a very pragmatic. He wanted to give very simple questions, and he liked, a small truth was much more valuable to him over a large truth we never reached. And in the case of this first image, what we've done is we have shown that black holes are likely to exist. Actually, there is something that that smells, that behaves like a black hole. Maybe it is a black hole. And this is really a change between before and after, because now we have a tool to actually take photos of black holes. And now we can start asking questions about, is there an event horizon? How big it is? Is there really a black hole? Or could it be something else, a wormhole, a boson star, a naked singularity? Before this image, all of these were plausible and equally plausible hypotheses. Now we know that some of these hypotheses are not just realized in nature. They are physically and mathematically possible, but nature has decided not to put a boson star in our galaxy, or to put a wormhole in our galaxy, because they would have looked different. So it's really a manifestation of the scientific method, and now we can use this method finally also for black holes. So it has changed the way I can teach about black holes. Before I was just writing equations on a blackboard. Now I can say there is this equation and there is this evidence that this equation is actually right. About whether it's accelerators will produce black holes. Okay, so this is a reasonable question, because one of the equations, maybe the most famous Einstein's equation, says E = mc squared. So the idea is to put in a very small volume a lot of energy. That's what happens when you crash two particles at very high energies. You condense in a small volume a lot of energy. And again, Einstein says, well, when you do this, you can produce a black hole, because producing a black hole is all about concentrating enough energy into a very small volume, or if you want, curving space-time sufficiently enough. So this is something that is, plausible, but then you have to calculate how much energy you need in order to produce such a black hole. Or, if you think about curvature, how much energy you need to bend space-time to the amount that you need in order to produce a black hole. And you find out, when you do this calculation, that our accelerators are like, a fly hitting a train. It's just so small, the energy are so insufficient that there is just no way of actually producing a black hole. Maybe if we manage to survive as a civilization for 1,000 years or so, we will be able to produce black holes through accelerators, but our technology is way too primitive to do this. But it's something that we can do, and maybe we will do this. It would be nice to produce black holes, because black holes have a lot of energy, and this energy can be exploited. There are ways of exploiting energy. So again, picking up what was mentioned at the beginning, what we're doing now may be dictating the technology that will be used by, generation in 1,000 years, because they will know how to produce black hole, and they will have managed to get the energy out of black holes to produce electricity or whatever. So, yeah, that's my answer to this.
The next discoveries. So your fields look now so close to each other, but still they are very far from each other. The infinitesimally small of the small world of particle physics, and the infinitesimally big world of galaxies and stars. So what is the discovery in the field of the other that would make a breakthrough also for you?
I'm excited by the progress in astroparticle in general, in cosmology. In the last 30 or 40 years, there has been a huge amount of progress, much more than in our field. This is my prejudice, maybe. And I dream of having discovered this new tool, which is the gravitational waves. No, it's really a new astronomy. No, you look at the universe with another tool, which is extremely powerful, and is complementary to all the other tools, the visible astronomy, the X-ray, the radio astronomy, all the other tools stay there. In addition, you have this new tool that, for example, our understanding of the very first stages of the universe, of the Big Bang, the origin of the universe, is limited by the fact that we use light, the cosmic microwave background, which is everywhere in the space, is an incredibly rich source of information. And we have been able to studying it in detail with extremely sophisticated tools to go back in time and really extrapolate the very, very first beginning of the universe. But the limit is the wall, is the the time in which light separated from matter, which is 380,000 years after the Big Bang. So this wall limits our capability to go back in time with clear understanding. But gravitational waves, they did separate from matter since the very beginning. So I imagine if the current theories that describe the origin of the universe through the cosmic inflation, so in a very fast expansion of a small bubble of the quantic foam that was at the origin, produced this huge expansion. If this is the correct description, we should have something imprinted in the gravitational waves, no? Is now hidden in the background. No? The entire space-time of the universe still resonates slightly of this origin. No? So I dream of the time in which the new generation of gravitational wave detectors will be able to identify this noise of the baby universe that will describe what was happening not at 300,000 years after the Big Bang, but just at the very, very beginning, in the inflation era, that would give us an additional tool to explain what was happening at the level of 10 to the minus 35 seconds after the Big Bang.
So, this way of looking at science, according to scales, is a bit old-fashioned, and it is a type of fashion that I was exposed to when I was a student. When I was a student, you either studied particle physics or you studied astronomy and astrophysics. What we've learned over the last 10, 15 years is actually that these two worlds can really talk to each other and provide information that are missing when one is just working in one field. Astroparticle physics is one example. And we know now, for instance, there are tools where we can look at the stars, we can look at galaxy and tell something about dark matter and help people who are looking for dark matter to explain what are the ranges in masses. We can look at two neutron stars merging to produce gravitational waves and learn something about what is the state of matter when it is highly compressed and very hot, whether it can produce a quark gluon plasma. So this is the beauty of modern science as we are living it now. There are many different ways in which we can answer a question, which is in the past used to be just one way. Now we have many different ways, and I think this is what we are doing now, creating scientists, young scientists that are able to understand not only particle physics, but also gravitational physics, astrophysics, and maybe they will be much better than us in trying to solve some of these mysteries about dark matter, dark energy, black holes, and so on.
Thank you very much. Let me come now to your books now. Writing books like yours is a way to fascinate the readers and bridge the gap between fundamental science and the wider public. So how did you jump from physics review letters to popular scientific literature, and what will we find in your books? I can assure you I've read them, not so many questions, and well explained, if at all.
No, in my case, I did so first I wrote my first book 6 years ago, 7 years ago. So I'm quite old. So during the activity that I had no time to not even to think to write a book. So I discovered the Higgs boson after 40 years of effort. So I don't want to bore you, but I can guarantee you that it was a frantic time in which we were passing through all possible crises, all possible disasters, and no idea to have just 5 minutes to think of a book. So I was convinced by friends to write a book after the discovery, when basically, I mean, the job is done. This was my view, and since basically the thing that we know as a scientist of nature are beautiful. No, so my attitude, my personal attitude is this one. I know things that most of the people don't know, and this is due to the fact that we have spent tens of years in developing tools, mathematics, quantum equations, that we understand things that the normal public don't understand. But those concepts are so beautiful, believe me, are fantastic. There is no science fiction that can compete with modern science. There is no competition in creativity, imagination, beauty of those concepts that we were discussing before. No? And so my push was I should share this with my friends, my community, my city, my and I decided to do it. We had many friends with colleagues, and when you have the dinner with friends, most of them ask me, what is the Higgs boson, what is the origin of the universe, what is exactly matter, what is the end of the universe, and I was trying to explain them without using any equation, the concept. So basically, I wrote books removing all the equations because this would have created a barrier for the readers, and using only the concepts, if you go to listen to a concert, you don't need to know all the details. Better if you know music, and if you are a composer, or if you know how to play an instrument, you understand much better, clearly. No, but even if you have you just have some education in the hearings, in listening. No, if you are educated enough in listening, and maybe somebody explain you exactly what are the most important elements of a certain symphony, you appreciate it without being an expert. The same could be done for science. I have the impression that exactly the same can be done for science, and my duty is try to forward you, the readers in general, the heart of the beauty of modern science.
So in my case, it was really COVID. Yeah. But I actually caught the virus much earlier. I got the virus about 10 years earlier, because I was teaching in a Master of Science Journalism in SISA in Trieste. And that's when I learned that, our job as scientists doesn't end with communicating to our peers, our colleagues. That's what we do, and we think our job ends there. We find a news result, we publish it in the scientific papers, all of our colleagues read it and understand it. And already then it was clear to me that that's not our job. Our job has another layer. And this layer is not just communicate to your peers, but communicate to your employers. Now, because all of you are my employers, I work for you. I have the privilege of doing the most beautiful job I can think of, but it's just because you pay me to do this. And it's a way of returning some of this privilege by explaining also to you what is it that we are doing. And I share Guido's view, us scientists think, I'm just too busy, forget about it. I don't have the time to do this. And that was also my attitude since I caught the virus in Trieste. But COVID, put me into the position of not moving so much, not having all the other duties, and spending my time in things that would otherwise take my time. And so I found the time to actually sit down and write what I knew about gravity and why it is so irresistible as a concept. Because, again, as Guido said, what we're doing is so beautiful. We have to share this beauty in a way that is comprehensible, not just to our peers. So, yeah, I thank you for allowing me to do this job, and this is just a way of thanking you back.
Okay. Obviously now we are all fascinated and confused, But this is what these conferences are all about, bringing us the fascinations and the mysteries of fundamental science and giving you a reason to, a further reason, if you need any, to move further with your research and with your science. Now, I beg you all, if you have questions, speak up. Their speakers are here because we are all wondering about what would come next.
Very nice. Yeah.
You spoke about dark matter. Can you elaborate the difference between dark matter and dark energy? And a second question, you said that you are not even sure that dark matter would be particles, so that it would be really matter. Could it be that in the end, dark matter and dark energy are the same, as also energy and matter are correlated somehow?
So this is a very good question. Let's say from a pragmatical point of view, dark matter and dark energy manifest themselves in different ways, but they could be related. So dark matter is needed to explain why galaxies are spinning faster than we see. Dark energy is needed to explain why the universe is behaving as it is now. In particular, the universe is expanding, but at an accelerated rate. It's expanding faster and faster. And that can only be due to some form of energy, which all of a sudden becomes the dominant form of energy. So dark matter and dark energy are really different things, although they share the adjective dark. Now, if they have to do with particles and understanding the nature of particles, it could well be that dark matter and dark energy have very deep roots together. But right now, when someone is trying to solve the dark matter problem, is not trying to solve the dark energy problem, and vice versa. So they are really, really different. One possibility that is interesting and is emerging as an interesting possibility is that dark matter is actually made of black holes. Teeny tiny black holes, so small that maybe we can even detect them on Earth. They would go through Earth without making much of a damage. You would say this is crazy, but it's actually plausible. Whether it is possible or not is still unclear, but there is nothing. We have a very narrow window where these black holes can have a mass, and so far this window is becoming thinner and thinner, but it's still there. So the one possibility is primordial black holes. These are black holes produced very early in the universe.
Not much to add, but for example, one search that we perform is we look for the production of microscopic black holes, not the one that would have destroyed the Earth, that were feared at the beginning, but tiny black holes that could be produced within the collisions of LHC. The current idea is that they will evaporate immediately, and we have a clear idea what will look like an event in which a micro black hole would have been produced at LHC. It would be a fantastic event full of particles produced like an immense fireworks. And the idea is nice because there is an idea connected to gravity that would solve additional problems. For example, gravity is too weak. No, is by far too weak. No, there is no way to deal with gravity because the intensity of the force is too weak with respect to the other normal forces, which are much stronger. But there is an idea that is elegant and intelligent, which says gravity appears to be too weak. Appears to be too weak, for example, if you assume that our world is limited to the 4 dimensions that Einstein described, the 3 spatial dimensions plus time. If there are additional space dimensions that were active, living at the beginning of the universe when there was enough energy, and then they have closed and they're not anymore present in our world, then gravity that developed itself in all the other dimensions could have been strong as similar to the other forces. For example, is one of the speculations that are under scrutiny. No? So the idea is that maybe if you use enough energy, you are able to open additional dimensions, and you are able to open a world in which gravity is stronger than the gravity that we experience in our macroscopic world. In a macroscopic level, gravity has not been yet investigated, so we don't know yet if at a very, very microscopic level, gravity is a weak force. No? So suppose that there is a threshold in which beyond that door, gravity becomes stronger. Then you will see the stronger gravity with the production of these tiny black holes that are formed within the collisions that we produced. Again, so far we have not yet been able to discover nothing similar, but this gives you an idea of how things are really connected. No? The investigation of the microscopic black holes that have masses of millions, if not billions of solar masses, and microscopic black holes that could be so tiny that to be produced within the LHC collision, and if discovered, they could become maybe possible candidate also to discover additional mysteries. Really, the two fields are so connected and so fertilized one with the other, with the additional discovery, that is like opening a new era of science. No, I have the impression that with the last 20 years, the two fields of science that were considered separated, the astronomers and the particle physics, are now different teams working on the same targets, on the same goals. No, yet you will need to, because the range at which dark matter acts is a macroscopic range, is not a microscopic range, but we would have an additional tool to understand.
Thank you very much for both of you for the excellent presentations. I have to apologize, I'm not a physicist, or I'm a chemist by training, so my question is maybe humbly a little stupid, but I'm fascinated about what you said about gravity being such a long-ranging force and apparently maybe very weak, at least we describe it in confronting to the other forces we know. My question is, if we limit ourselves in our imagination for the dimensions we know, so 3-dimensional plus time, and we see the two concepts like a gravitone, I understood, a corpuscular nature of gravity, and the curvature of space-time. Is there anything in this field, this 4-dimension, which could combine both theories, or are there more or less standalone approaches for the same subject?
Well, we think anything that will come out has to match these two worlds and these two descriptions. We certainly think that Einstein's theory, as described in terms of curvature, is right, because all of its predictions are right. We also think that fundamental interactions are well described in terms of particle description, quantum mechanical quantum description. So the idea is putting together these two worlds, and the problem is putting them in a way which is reasonable and mathematically correct. And so far this has not happened. But in either case, we want to preserve what we know is true and work well: quantum mechanics and general relativity. And that's the difficulty. Maybe that's the problem. Maybe the source of the problem. Maybe we should just say, forget about it. We have to come up with a completely new description which doesn't try to save anything. That's a possibility.
I'm excited by this perspective that behind this difficulty there is something emerging completely new. No? the fact that we are not able to couple these two visions, I would couple to the fact that quantum mechanics that we use daily, in our work is the kingdom of quantum mechanics. It works perfectly. But first of all, we don't understand why. And secondly, there are too many things that are completely mysteries. So quantum mechanics is based on principles that nobody is able to explain. The uncertainty principle, the exclusion, the Pauli principle. So we are here because our orbitals are organized following a principle that nobody is able to describe. Why electrons sharing, having the same spin, cannot occupy the same orbital? I have no idea. This is not applied to photons. In a laser light, in a pointer that I use to a blackboard, I have an army of photons sharing the same quantum numbers. But in the orbitals of each element of matter, this law is not valid. Why? No idea. Entanglement is another example. Again, we measure this phenomena daily in producing pairs of particles which are connected in a way that is completely mysterious. So the idea is that again, quantum mechanics works, but we are at the surface. We are like floating on an ocean and we see only the surface. But there is something appearing on the surface which has some connection downstairs, and we are until the moment in which we don't dive and try to understand what is producing the emerging symmetries, the emerging conservation principle, we don't understand exactly. So it might well be that there is the need of a new theory, completely new theory. And I would be happy if I would be alive at the moment in which somebody will be able to produce the new theory and somebody will be able to find the first evidence of it. When these things happen, usually in the past, a new theory has emerged. We have not corrected here and there a few elements. It's like a catastrophe, something emerging, explaining, but it was trivial, it was simple. How we have missed it? And so the message to the young people that we give in our work is this: think out of the box. Maybe you will be the person that will be able to solve what Albert Einstein or Stephen Hawking were not able to discover. It's up to you to try, and this is exactly the kind of change in the paradigms that sooner or later will happen also in our field.
Thank you very much to Guido and Luciano again. This think out of the box is really the best message that we can give to ourselves and to the next generation.